Okay, our next speaker this morning is Kirill, who will speak on the shapes of rational numbers.
Okay, thanks very much, James and Sergey and Ilya, for inviting me to this conference. It's always a thrill when someone wants to hear about what I'm working on. I should also thank my wife, even though she isn't here, because she's willing to watch the kids the first week of classes while I'm here on vacation, essentially. The only other joke I wanted to make is that I'm speaking on a paper which is, I checked 48 pages. So my original plan, since it's a 50-minute talk, is to just read you 1 page per minute. But I decided against it. So we'll talk about Lemniscates. So the first thing we'll do is write a definition of a Lemniscate. If you can't see, let me know. So let C be a positive number, and P a complex polynomial and 1 complex variable. Then we call set Z such that the absolute value of P of Z is this given constant, a polynomial Lemniscate. So it's just the pullback of a circle under a given polynomial. A pullback of a circle centered at the origin of whatever radius you would like. So also, I can tell you the main question we studied in this project, or at least a simplified version of it. What can a polynomial Lemniscate look like? Sure. I'll write it over here. Can you see the definition? Yes. Okay. So the question is, what can a polynomial Lemniscate look like? Look like is, of course, a little bit ambiguous. The follow-up question, which we should always ask ourselves, is why should we study this? Looks a little bit like a question out of the blue. Well, why don't we pull back something else under a polynomial? Why a polynomial and not some more general function? But the first thing I'll do is convince you that this is actually a rather fundamental question with some interesting applications. So first, all these questions 1 and 2. So first we'll answer question 2 before we answer question 1. But we'll give one answer to question 2. So one answer to question 2 is in polynomial approximation. So suppose we have a compact set, and here I'll start using colors. I'll do it here. So we have a compact set K. It's compact. And we have that K is contained in some open set, white, our open set U. And we have a function which is holomorphic in U in this neighborhood of the compact set. And we want to approximate this holomorphic function in a neighborhood of our compact set by a polynomial. So where do Lemniscates come in? Well, they come in the following sort of supposition, and I'll explain this later, but for now it will be something we're going to suppose, and we'll see that the supposition leads to some interesting consequences which justify the study of polynomial Lemniscates. So suppose there exists a polynomial Lemniscate. Let's use another color, maybe blue. Gamma. So set z such that mod p of z equal to 1. We'll take our constant to be 1, which we can always do by rescaling, so that the Lemniscate separates the boundary of our open set from the compact set. So suppose there exists this polynomial Lemniscate separating boundary of u from k. So not to spoil the story, but there does exist such a polynomial Lemniscate, and this is not our result. I'll give you a little bit of information on that in a minute, but for now, what does this buy us with respect to polynomial approximation? Well, it's all summarized in the following formula. So we've had a few beautiful pictures, and here is a very beautiful formula. It's not our formula. I'll explain a little bit of the history in a minute. Consider the following expression. So f is the function we're trying to approximate, and then we subtract off the following integral, 1 over 2 pi I integral over this polynomial Lemniscate. Maybe I'm going overboard with the colors, but let me try and stay consistent. We're integrating over this polynomial Lemniscate f of zeta over zeta minus z. This almost looks like the Cauchy integral formula, but we have this extra term, which is the polynomial appearing in the definition of this Lemniscate, p of z over p of zeta raised to the nth power. We also want to add an n subscript here. N is a positive integer, and the variable of integration is zeta. So with regards to this picture, we should think of zeta as lying on this blue curve, and z is something inside k. So two remarkable things about this formula. One is that this is a polynomial, which is of course not obvious whatsoever because this is an integral. And the other, well, it's an integral where a z appears in the denominator. So it's not obvious that it's a polynomial in z. The other thing is that this is in fact an approximant to the function f. So two things are true. And by the way, please feel free to interrupt me at any point if you'd like clarification or would like to ask a question. So two things are true. One is that q sub n is a polynomial. This isn't so hard to justify. If we use the Cauchy integral formula to write f of z as 1 over 2 pi I integral over the same curve, f of zeta over zeta minus z, we can bring everything into one integral. And when we add our two fractions here, what we get is that q sub n of z is equal to the following expression. So it's 1 over 2 pi I integral over gamma. The f term factors out, and we have Pn of zeta. So the nth exponent is not an iterate, it's a power. Pn of zeta minus Pn of z divided by zeta minus z times the nth power of p of zeta. So this is just when you add those two fractions. And the integral is with respect to zeta. Now, this is a polynomial in Z because if you plug in zeta equals Z, of course, the numerator vanishes. That means you can factor out a zeta minus Z term from the numerator, and that's going to cancel with the zeta minus Z term downstairs. So in fact, there are no Z's downstairs. And so you can bring all of the Z terms outside of the integral, and you see that this is a polynomial in Z. The other thing that I wanted to, well, that makes all of this relevant is that Qn approximates F on the compact set K. This also is not so lengthy of an explanation. If you want to bound Qn minus F, well, of course, this F term will cancel, and so you're just left with how do I bound the absolute value of this integral? So I'll just do it here. So when we bring the absolute value inside, so zeta minus Z, because zeta is on this curve, which separates the compact set from the open set U, the distance between zeta and Z is going to be bounded away from 0. So this denominator is bounded away from 0. This F term, it's bounded by whatever the sup of F is. And okay, the 1 over 2 pi I term is constant. When we integrate over gamma, we get the length of gamma. Nothing too interesting yet. Where the polynomial Lemniscate comes in is when we bound this term, P of Z over P of zeta. Well, when we look at the absolute value of let's look at the denominator first. When we look at the absolute value of P of zeta, well, zeta is on this curve, which by definition is where the modulus of P is 1. I should have put zeta here, not Z's. It's not technically incorrect, but maybe poor exposition. So this denominator is just 1. So the bound here is whatever the bound of the modulus of the polynomial is over the compact set. So all of this just gives us that up to a constant, this is bounded by whatever the sup is over K, the polynomial raised to the nth power. And just by the maximum modulus principle, if P has absolute value 1 on this curve, then P has absolute value strictly less than 1 on this compact set, and that number is something strictly less than 1. So this is less than C to the n, which gives us this nice rate of convergence. It's a rate of convergence because you can also calculate the degree of this polynomial Q sub n, and this rate of convergence is sharp in a particular sense. So this is all to justify why polynomial Lemniscate, or one reason why polynomial Lemniscates are of interest, and in particular why this question of what can they look like is of interest. It has this very, I think, fundamental application to polynomial approximation. So it's kind of fallen a little bit out of fashion, maybe polynomial approximation, but it's still a very fundamental question. So let's see what I want to say. Yeah, so suppose there exists a polynomial, and suppose there exists a polynomial which is a Jordan curve separating the boundary of U from K. If in this setup there were some other components over here, in fact, that wouldn't mess up the argument, but it would make the statement less clean. Maybe give me one more minute to give you a precise statement, and it will clarify things a bit. So, right, when I found this formula in a 1934 paper by Joseph Walsh and Helen Russell. It was quite mysterious to me and remained quite mysterious to me for some time as to where it came from. And I gave abbreviated versions of this talk where I said, well, we use this, but I embarrassingly enough, don't know really the history behind it or where it came from. But there's this nice book on approximation by Nick Trefethen where, among other things, he gives a really detailed history of things like this. So this formula is essentially due to Cauchy. It appears in an 1826 paper. In a journal, the journal citation is Exercices Mathématiques, which, as far as I know, is no longer around. And where he used it, there was no n, and the curve was not a polynomial lemniscate, but just some contour which surrounded the zeros of the polynomial p. And in that case, this exactly gives you an integral formula for the Lagrange interpolating polynomial. So if you have a function and you want to approximate it by a polynomial which agrees with the function or interpolates with the function at n points, you can write that polynomial as this integral formula. So there were later improvements to Charles Hermite, who put this exponent n here and said that with this exponent, you get interpolation not just of the functional values, but also of the functional derivatives. And this idea of integrating not over some arbitrary curve separating or containing the zeros of the polynomial where you want to interpolate, integrating over the polynomial lemniscate to get a polynomial approximation, that idea was due to David Hilbert in 1897. And this was published, right, Hermite's result was published in Kirill's journal, which is still around. Hilbert's result was published by a journal whose name is in German, which I won't attempt to pronounce, but as far as I know, that journal is not around either. So we start at 10:45. So this took 20 minutes. Okay, not bad. Right, so does there exist such a polynomial lemniscate, right? So question, you can call this question 3. Does there, let me say always, exist gamma as in the previous arguments? So given a compact set and a neighborhood of that compact set, can you always find a polynomial lemniscate separating the compact set from the boundary of that open set, as in the previous argument? One other thing I forgot to mention, which maybe makes all of this a little bit less mystifying, or at least it did to me, is, well, you can think of the simplest case in which we might do this argument. When is the simplest case? Well, what about when K is just a Euclidean disk and U is a Euclidean disk? If you go through the argument and you do a couple of calculations with the residue theorem, what this polynomial Q sub n is doing is it's just truncating the Taylor series of approximation of F. So in that sense, all of this, these approximating polynomials are just generalizations, suitable generalizations of the Taylor series approximation. Right. So the answer is yes, and this result is given a name. It's called Hilbert's Lemniscate theorem, and it has been it has attracted some attention. So let me maybe say, at least in words, since Sergey asked, a little bit more of a precise statement. A little bit more of a precise statement is, okay, you give me a Jordan curve, and I want you to give me a polynomial lemniscate which is a Jordan curve. So there's only one component. And so that the polynomial Lemniscate looks like the given Jordan curve. So I said I was going to be more precise, but of course looks like it's not more precise. And actually, it's a little bit more challenging than you would think to make this statement precise, because you might think, well, let's just use the Hausdorff distance. But if you have a Jordan curve like this, let me connect it. If you have a Jordan curve like this, you can approximate it by another Jordan curve in the Hausdorff metric, which looks like this. So these two things are close in the Hausdorff metric, but this mode of approximation is completely useless when it comes to this argument over here. So actually, it takes a little bit of thought to make this precise, and what notion of approximation is actually appropriate and useful. We'll talk about this in a few minutes when I state our actual result. So the answer is yes, it's due to Hilbert, and this polynomial approximation application is why he studied this. I was also tempted to mention a dynamical application, but let me maybe keep that in the back of my mind, and if I have time later, I will mention it. Right, so roughly, so before I state a little bit more concretely our question, what we're studying is this case that the polynomial Lemniscate looks or is a Jordan curve is not usually going to be what happens, right? You can get kind of a visual or an intuitive understanding of polynomial Lemniscates as follows. So if you have a polynomial P and you just look at its zeros, well, when that constant C over here is really small, what is the pullback of a small circle around the origin going to look like? Well, it's just going to look like a bunch of small Jordan curves, wiggly Jordan curves around the zeros. So it's not going to be connected, certainly for small c. And on the other hand, so this is c small, on the other hand, when c is big, you're pulling back, all the dynamicists do this all the time. You're pulling back a small circle under a map which is basically z to the n near infinity. Of course, you are just going to get a really big circle. So this is what the Lemniscate looks like for c big. And how does it go from being a bunch of small circles to being one big circle? Well, the really interesting thing happens when the circle in the image passes through a critical value, or equivalently, when these different components of the Lemniscate pass through a critical point of the polynomial. Right, so the picture is like these things kind of grow for a while, and the topology stays the same, but then, whoops, at 1 second, two of these components merge, and we get something which is topologically different. And this, let me emphasize, is a critical point, right? Because this is the only way the topology can change, and these things keep merging. Maybe several of them merge at once until we get one big circle, and then the topology stays the same. So again, back to the original question, hopefully having justified why this is not just some random question we picked out from a big bucket of questions. What can a polynomial Lemniscate look like? Well, Hilbert's result can roughly be described as saying it answers this question in the case that you're assuming the Lemniscate is a Jordan curve, right? So Hilbert's result says that if you draw any Jordan curve, there exists a polynomial Lemniscate which looks really close to that Jordan curve. This is kind of an incomplete answer, right? Because Lemniscates are not usually Jordan curves. Not only can they have other topologies, but generically they're not even going to be connected. So this hopefully explains our central question, okay, Hilbert did the case of a single Jordan curve, but now suppose you have something more general, which has no topological obstructions to being a Lemniscate. Can you approximate it by an actual Lemniscate? And the answer is yes, and that's roughly a verbal description of our main theorem. So let's see, in my notes, what do I want to say next? Right, so let me put the definition of what a topological Lemniscate is, and our result will be any topological Lemniscate can be approximated in a precise sense by a polynomial Lemniscate. Let me also say in passing that the setting in which we worked was not really about polynomial Lemniscates, but it was about rational Lemniscates. And I'm just restricting to the case of polynomial Lemniscates because the pictures are a little bit simpler and our results are already new in the polynomial setting. So I'm trying to avoid kind of putting too much information out there at once. So even though we worked in the rational setting, I'm kind of focusing on the polynomial setting for this talk. Right, so central definition, which kind of replaces the role of a Jordan curve in Hilbert's work, is the following. This is not the definition you'll see if you read our paper, but I think it's a more appropriate definition for a talk. So a topological polynomial Lemniscate is just something which is homeomorphic to a polynomial Lemniscate via a homeomorphism of the sphere. Is a homeomorphic image. Phi of the set Z, where mod P of Z is equal to C. For phi, a homeomorphism. I had the bad luck of having my talk scheduled while they're cutting the grass. Okay, so right, it's something which has no topological obstructions to being a polynomial Lemniscate. So can draw some pictures. So figure 8 is fine. You can have more lobes. So you can have not very good at drawing. Don't have much practice lately in drawing these pictures, although I drew lots of them when we were writing up the paper. So we can have several lobes. We can have several components. This, all of this is fine. So something which is not fine is something like this, an open arc. Why is this not fine? Well, how could you get a polynomial which maps this onto the circle? Something is going wrong at this point, right? Because if you look at a neighborhood of this point, polynomials up to changes in the domain and range up to coordinate changes, mapping is always just z to the n, and usually it's just n equals 1. So this picture cannot be mapped homeomorphically onto this picture, but for n equals 1, but even for n equals bigger than 1, when you pull back a segment, you get a picture which looks something like this. So something like an open arc. This is not. This fails to be a polynomial Lemniscate for a topological reason. So this definition is just saying, okay, throw away anything which fails to be a Lemniscate for topological reasons. A more intrinsic definition is also, so if you look at the paper, what we write is a more intrinsic definition which has no reference to polynomial Lemniscates. You can define it, I'll say it in words, it's a bit cumbersome to write down. you just say, okay, you have a set such that there are finitely many points, which are these vertices, so that if you remove those vertices, you're just left with finitely many components, each of which is either a Jordan curve, like this guy, or an arc connecting two distinct vertices, or an arc connecting a vertex to itself. So with this intrinsic definition, it's equivalent to this definition that I wrote down, and the proof is just the measurable Riemann mapping theorem. So if you have such a picture, which doesn't fail to be a Lemniscate for obvious topological reasons, you can define a branched cover which maps this topological Lemniscate to a circle. And then when you straighten, maybe let me do this on the next board. When you straighten the picture using the measurable Riemann mapping theorem, we abbreviate it MRMT, you get a picture which is homeomorphic to your original one. Give me a minute to draw a homeomorphic copy. But of course, now it's been distorted. But when you look at this composition, it's a polynomial. This is the measurable Riemann mapping theorem. So if you have any topological polynomial Lemniscate, either by definition or by a quick application of the measurable Riemann mapping theorem, you have that such a topological object is homeomorphic to an actual polynomial Lemniscate. Roughly, our central result can be described as this homeomorphic polynomial Lemniscate can actually be taken via a homeomorphism which is as close to the identity as you would like it to be. So let me phrase this a bit more precisely. I think this is what I want to say next. Right, so theorem. This is the polynomial version of our central result. Bishop, Aramenko, L. Right, so take one of these topological Lemniscates. Let G be topological polynomial Lemniscate. Then there exists actual polynomial Lemniscate. Which is homeomorphic G via a map C, a homeomorphism, self-homeomorphism of the sphere. So far, this is just a quick application of the measurable Riemann mapping theorem. But this last thing, that you can take phi of z to be as close to the identity as you would like it to be. That's the new thing. So which norm? Well, it depends if you're on the sphere or the plane. Either way, you can take it as close to the identity as you would like it to be. This is a general, well, it's more, I would like to think, than a generalization of Hilbert's theorem, but it includes Hilbert's theorems, right? So there you had just a Jordan curve, and you can find a polynomial lemniscate which has the same topology, namely is also a Jordan curve and approximates the given curve. So our result is basically saying the same thing, but it includes all of these extra topological possibilities which can occur for polynomial lemniscates. So I like to think of it as a pretty complete answer to this question of what can a polynomial lemniscate look like. So basically, if there are no topological obstructions to it being a polynomial lemniscate, to your object being a polynomial lemniscate, then an arbitrarily small perturbation and homeomorphic perturbation is actually a genuine polynomial lemniscate. So I still have about 20 minutes. So let me make a few remarks. It's definitely not unique. There's if you wanted a uniqueness statement, you could say, okay, I want only a degree 17 polynomial approximation lemniscate, and then you might be able to get a uniqueness statement. But this never really occurred to me as an avenue to pursue. I know the joke about mathematicians is you give them the question of what does 1 + 1 equal, and they say, well, I don't know the answer, but I know it exists and it is unique. But I don't know I don't know a sensible way to get a uniqueness statement out of this result. Right, a few remarks. So I wanted to mention some applications maybe of this result. So I talked about polynomial approximation. We got a new result about rational approximation, which kind of suitably generalizes this previous theorem that I wrote down and have now erased. Suitably generalizes in the sense if you allow your compact set to have holes now, then in order to approximate, you can't always do it with polynomials. You need rational ones. But the rational approximations, you can take them to have the minimal possible number of poles, and you can prescribe those poles appropriately. And there again, there's a sharpness to the estimate, and essentially the proof was replacing p in this integral formula that I told you about by r, and looking at rational lemniscates rather than polynomial lemniscates. So just in words, that's one application. The other application, which I wanted to mention, is this dynamical application I had kind of been tempted to talk about earlier, but skipped it. But now, now if you have, say, some Jordan curve, and to make it a little bit more, I don't know what's the word, a little bit more interesting, I can, can try and my best to draw something like a dog. So this is a Jordan curve I've drawn, and the question is there a polynomial whose Julia set looks like this dog? And the answer is yes. And Catherine Lindsay and Malik Younsi gave one proof of this based on Hilbert's Lemniscate theorem. The proof is just, okay, take a polynomial lemniscate, which looks like the given Jordan curve. That means either side of the Jordan curve over here is mapped to either side of the unit circle. So this is set mod z is equal to 1. And now post-compose with z to the 1000th power. If you look at this composition and you iterate it, if you normalize 0 to be here and infinity to be outside, then there's going to be an attracting fixed point near 0, and there's going to be an attracting fixed point near infinity. And it's not going to be difficult to prove that if you're a little bit outside of the dog and you iterate this composition, then you get sent to infinity. If you're a little bit inside this dog, you iterate to this attracting fixed point here, and the Julia set has to look like this dog. So this was the other kind of application of this Hilbert's Lemniscate theorem that we found in the literature, and that we could also do something new with. Roughly what we did something new with is, okay, what if you have, so what they did actually is if you have several dogs, none of which separate any of the other dogs from the point at infinity, what we did is something like if you have nested dogs. So if you have something like nested dogs, is there a rational function whose Julia set approximates this set of nested dogs? So there you need poles. This brings me, right, so let me talk a little bit about rational lemniscates. A little bit, only a minute or two. What's the difference between a rational lemniscate and a polynomial lemniscate? And also I should mention that one of the reasons I'm talking about this, one of our organizers, James, has an interesting result, which says if you allow yourself not to iterate rational functions, but meromorphic functions with essential singularities, then you don't need any approximation at all. Actually, there is a meromorphic function whose Julia set is exactly that dog. So there's some kind of neat work there in the past few years on this approximation of compact sets by Julia sets. Right, so what is the difference between a polynomial lemniscate and a rational lemniscate? There isn't too much difference. Basically, the only difference is that when you allow yourself rational maps, you can have nesting of these components. Right, so a rational polynomial lemniscate basically looks like a bunch of disjoint curves, and there is no nesting. None of these curves sit inside of the other curves. Right, so this is polynomial. Rational lemniscates, you're allowed to have whatever nesting you would like. So you can have lots of components sitting inside lots of other components, and this can go on for as many depths as you want. Each time you cross two edges, there has to be a pole, because each of these complementary components has to map either to the disk or the exterior unit disk, and which of those two it is just switches each time you cross an edge. I should mention that the version of this theorem where you just have a bunch of disjoint Jordan curves, this was due to Walsh and Russell in this paper that I mentioned from the 1930s. They proved that there is a polynomial lemniscate which approximates this given collection of disjoint Jordan curves in the suitable sense. And again, their motivation was a polynomial approximation. There are two things I want to say at once. One is that our result, kind of the proof, becomes much more difficult as soon as you allow vertices, for a reason which hopefully I will have time to explain. So what we also did was consider rational, the sort of appropriate rational version of this theorem. Okay, what if you allow nesting for your curves? Now, you can't do this with polynomial, you can't approximate them with polynomial lemniscates, but you can approximate them with rational lemniscates. So I wanted to remark that, as I'll talk about in a minute, actually the proof for the rational version of this theorem, again, where there are no singularities, there are no critical points on the lemniscate, the ingredients needed for the proof of that rational version basically have been around since Hilbert. So it is interesting that despite this really neat rational approximation application, no one had done this in the literature. And at first, when we put this paper out, I was thinking, well, maybe it's somewhere in some paper, maybe in a different language, and someone at some point will tell us, oh, this was already done. But by this point, I'm pretty sure that it hadn't been done, or it hasn't been done. And it's kind of curious, because if the ingredients have been around and there are nice applications, why didn't someone do it before? I think that my best guess is that you need a little bit of topological imagination to generalize this result from polynomials to rational functions. You kind of need to understand basically that for rational maps, poles play no distinguished role. as opposed to polynomials where they play a very distinguished role. There's only one pole at infinity. So even though all the ingredients there was just a little topological imagination, which was missing, but is pretty straightforward these days. Right, so from here would now be a good time to start talking about proofs. And let me just make sure that there are no kind of, there was one other broad remark I wanted to make. So there are these two applications I mentioned, polynomial approximation or rational approximation, and also to this Julia set approximation question. But in some sense, these are very dissatisfying applications to me because they only rely on a special case of our main result, which is much, much easier to prove than what we actually spent most of our time proving. So as I mentioned, but I'll mention it again, if you want to, and I'll explain this hopefully in the proof, if you want to just approximate a disjoint collection of Jordan curves, this is easy. But now if you want to approximate something where there are these critical points on the Lemniscate, this is much harder. I mention this because all of the applications that I know of these Lemniscates only rely on the much simpler case where each component is a Jordan curve. So I have this kind of question, are there any applications of the much more difficult version of this theorem, or difficult from the proof point of view, where, okay, we can approximate not just Jordan curves, but things with these singularities on them. None of the applications I know of rely on this, being able to do this much more difficult thing. So I'd be interested to know if there are any reasons why one would be, any places where one would want to apply this extra information about being able to do it not just for collections of Jordan curves, but for things with these singularities on them. Okay, so now let's talk about proofs. So in my defense, I already talked a little bit about some mathematics when I did this polynomial approximation explanation. Let's talk about the proof in the case when you just have a single Jordan curve or a collection of pairwise disjoint Jordan curves. Proof is roughly the same. And the ideas go back to Hilbert. So let me call this proof ideas. So suppose you're trying to approximate, I give you this Jordan curve and I'm asking you to find me a polynomial Lemniscate which approximates this Jordan curve. So I'll explain it kind of one of two ways, in kind of a very dry mathematical way, and then hopefully in a more intuitive way. So if this is your compact set K, mathematically what we do is we just look at the Green's function with pole at infinity. It can be recovered by integrating the logarithmic kernel against harmonic measure. So log mod z minus zeta. Zeta is on the boundary of K. Z we're thinking of as being off K. Log mod z minus zeta integrated against harmonic measure. There are some competing notations here. So the variable of integration comes first. The point where harmonic measure is based comes second. And for the complement of this compact set, now what we do is we discretize this measure. So harmonic measure, it's going to be a measure along the boundary of K, which gives no mass to any single point. But when we discretize the measure by kind of trying to imitate the measure by placing delta masses with different weights at different points along this curve, we get something like sum 1 over n log mod z minus zeta I. So these zeta 1 is here, zeta 2 is here, and so on. they're distributed according to trying to mimic harmonic measure. Now, if we multiply this formula by n times the green function is this sum, and log of a plus log of b is log of ab, right? So this is log of the product of z minus zeta sub i's, and this is a polynomial. This is the desired polynomial, because the level sets of this polynomial, they differ by constants, but the set of level sets of this polynomial is the same as the set of level sets of log of mod of that polynomial, imitate the level sets of the Green's function. And the Green's function is identically 0 only on your compact set. So g of z is equal to epsilon looks something like what you want, right? So this is g of z. So set z such that g of z is equal to epsilon. So this is the idea in Hilbert's work. As I mentioned, it already gives you also this idea. It gives you the polynomial proof, but it also gives you the rational proof with appropriate modifications and a little bit of imagination. Right, this is kind of the drier mathematical version of this proof. The more intuitive version of this proof is kind of, you imagine that your compact set is a metal, a conductor, and you imagine the complement is an insulator. You consider a sort of electric field on the sphere. Electrons are allowed to move around in this metal. They're not allowed to move around in the insulator. And you place a charge at infinity. What happens to the electrons in the metal? Well, they all try to get closer to the positive charge that you placed at infinity, but they don't all quite just go to the single point closest to infinity, because they also want to repel one another. So there's this sort of balancing of forces which distributes the electrons along the boundary, and the resulting distribution of electrons along the boundary is exactly described by a harmonic measure. So I wanted to say this approximation exactly holds off of the boundary of the compact set K. And from this physical point of view, it's kind of very clear, because what you're trying to approximate is an electric field generated by a continuous distribution of electrons along the boundary of K. And what you're doing is you're trying to imitate that by placing unit charges or appropriately weighted discrete charges along the boundary. And you can do this in such a way so that at some point, a fixed distance from the boundary, the charge felt on this point is not going to see the difference between a continuous distribution and a sufficiently fine discrete distribution. But this is always going to fail as you approach the boundary of K. Right, so this is the main idea in Hilbert's work. Right, so what is the difficulty when you're trying to do a similar such argument with vertices? So when the thing you're trying to approximate is not a union of Jordan curves, well, if it looks something like this, this is what you want to approximate. Now the issue for one is, if you just look at the Green's function with pole at infinity, the level sets are never going to cross as you want them to, right? So they're not going to be homeomorphic to what you started with, right? This is g of z is equal to epsilon. So what do you do? Well, what if we just erase this and put two disks which are really close over there, and two disks which are really close over here. So now the Green's function, the level sets, they do have to cross at some point. The trick is, or the difficulty is, how do you know that you can draw these things so that the level sets of the Green's function cross at exactly the same time, right? So maybe this one crosses at time 1/1,000,000, and this one crosses at time 1/10 million, what do? Okay, well, maybe draw these a little bit closer, so that this one crosses at time 1/10, the same time as this one, but changing this domain over here, that affects the Green's function over here. So now maybe this is crossing at the wrong time. So nevertheless, this argument ends up working, that you can draw not your original graph, but suitable changes, or I don't want to use the word perturbations, but suitable changes or adjustments of your original graph, so that you can make these critical points all happen at exactly the same time. There's some topological argument needed there. What we do from there is, okay, now we apply exactly this same result. We get these approximating polynomials whose lemniscates look as close as we want to the lemniscates, which are now homeomorphic to the and close to the picture that we wanted to realize. Then there's another difficulty. We just have approximation, but again, even for the polynomial, we need all of the critical values to have exactly the same modulus. And so maybe we get the right picture for the Green's function, but then this approximating polynomial, maybe it has the same issue. It looks a lot like it, but the critical values are just slightly off. If we choose the circle so that the critical value lies on that circle, for this critical point, maybe it doesn't happen for the other critical point, just arbitrarily close. So what we do there is we just go in a neighborhood of each one of these problematic critical points, which are just slightly off, and make a quasi-regular change of coordinates in the image. Then when we apply the measurable Riemann mapping theorem, we get, so the point of the quasi-regular change of coordinates is so that all of the critical values do occur at the right time, or the critical values all lie on the same circle. So we get a homeomorphic image here, which has the right properties. This is where this homeomorphism comes in, or one of the ways this homeomorphism of the sphere comes in the statement, that after we apply the measurable Riemann mapping theorem, we get the right picture, but it's slightly perturbed from our original picture. And we can do this in a way such that the quasi-conformal change of coordinates here from the measurable Riemann mapping theorem changes things as small as we want to, because the critical points are off by an amount which is as small as we want to, because now we're in a region where our approximating polynomial approximates this Green's function, or log of mod of that polynomial approximates the Green function. So just the last thing, even this case is much simpler than the case where we have vertices of higher degree. The step which is more difficult is how do you draw some subregion of this, not only so that all of the crossings for level sets of the Green's function happen at the same time, but even if they happen at the same time, it might look slightly off, like it might not be a single higher degree critical point, which is the picture that we wanted, but it might be two nearby lower order critical points. So this also requires some new ideas, and also quasi-conformal mappings are the hero that saves the day there as well. So my time's up, so thanks very much for listening.